All right, in this example, we're being asked to take the limit as x approaches infinity for x squared divided by e to the 3x. All right, so this is an infinite limit because the x is going to infinity. So let's see where these two functions are headed as the x's get larger and larger and larger. You can use a table if you need to, but I think with these we can pretty much use our intuition. As the x's get larger, I think x squared will get even larger, and so it's pretty clear this is going to go to infinity. And then e to the 3x, that's an exponential growth function, and as the x gets larger, this is going to get much, much larger, right? So this will go to infinity as well. So at first glance, it looks like we get infinity over infinity, which is, if you recall, an indeterminate form. 0 over 0 is another indeterminate form we get a lot of times. Infinity over infinity is an indeterminate form we get quite often. And if we get an indeterminate form like this, then we either have to use some sort of algebra to kind of simplify this guy. A lot of these, if you have a polynomial over a polynomial, you can factor and cancel things and things of that nature. But for ones like this, I don't see any algebra that we could do to simplify this very much. And so if that's the case, one thing that might be helpful or applicable here is something called L'Hopital's rule. L'Hopital's rule is a great rule that helps you evaluate limits when you have infinity over infinity or 0 over 0. Most instructors would ask that you write like a little LH, right, or a little star or something to indicate that you're about to use L'Hopital's rule. And what it says basically is that you can differentiate the numerator, differentiate the denominator, and then repeat the limit, and the limit will be the same thing as the original limit. All right, so let's try L'Hopital's rule here. So we take the limit as x approaches infinity. The numerator would be 2x, and the denominator would be 3e to the 3x, right? Differentiate the numerator, differentiate the denominator. Now we can repeat this limit, and hopefully if this gives us an answer, then we'll be done. Let's see. I'll change colors here to differentiate it from the green. All right, so as x goes to infinity, I think it's pretty clear that 2x will also go to infinity. And the denominator, again, unfortunately, is exponential growth, so I think that's going to go to infinity as well. We get another infinity over infinity, so that's another indeterminate form. And so what do we do now? We haven't seen one like this yet. Well, it's totally allowable to repeat L'Hopital's rule as many times as you need. The only criteria is that it has to be infinity over infinity or 0 over 0 period. If it's 5 over infinity or 0 over 7 or something like that, you can't continue to do L'Hopital's rule again and again. But hey, we got infinity over infinity, so I think we can just do this one more time. Let's see what this yields. We use L'Hopital's rule one more time. The limit as x approaches infinity, the derivative of the numerator is going to be 2 this time. The denominator would be 9e to the 3x. That's a little chain rule here. All right, and now let's see what this limit is going to be. 2 is a fixed constant, right? 2 is going to just stay 2. There's no x's at all in that numerator. And then as the x's get larger, again, the denominator is still exponential growth, so it's going to grow and grow and grow. And just basic algebra, if you have a fraction with a fixed numerator but a really large denominator, it's going to get closer and closer to 0, right? The larger the denominator gets, the fraction goes to 0. Just think of something like 1/10 compared to 100th or 1,000th or 1,000,000th, right? It gets closer to 0. So this limit will certainly approach 0. So 0 is our final answer for this problem, and the way that we got it was by using L'Hopital's rule.